Morning, everybody. Welcome, a very hearty welcome to the first in-person Clay Research Conference since 2019. I hope you're all feeling the joy of being together again to do mathematics. We certainly are. It promises to be a day of exciting mathematics with some of the highlights of what's going on in the world. I hope you all enjoy it. I don't want to steal too much of your time, so I'll hand over to Mike Hopkins to introduce our first speaker.
Thank you, Martin. I haven't been called upon to introduce speakers like this very often. I was advised just to look at the Wikipedia and read from that. And when I did that, I learned that Bhargav Bhatt plays cricket in the Indian Domestic League and that he's a slow left-arm orthodox bowler. So he's also widely known for his deep and influential mathematical work. His work with Matthew Morrow and Peter Schultz on p-adic Hodge theory, his proof of the direct summand conjecture in commutative algebra, and the derived de Rham cohomology and prismatic cohomology, the latter of which is work with Peter Schultz and Jacob Lurie. He was a professor at Michigan until 2020 when he moved to Princeton and the Institute for Advanced Study. And he's recently received quite a number of awards. In 2021, he received the New Horizons Award as well as the Clay Math Award. And in 2022, the Nemers Prize. So I give you Bhargav Bhatt.
Thanks a lot for that introduction and for this invitation. I used to play cricket, but not at that level. Okay, right, so I want to talk about, I think the title of my talk was Vanishing Theorems in Algebraic Geometry. And more precisely, I want to talk about vanishing theorems for cohomology in algebraic geometry. And so let me just spend a minute telling you something about cohomology at some very vague level. So it's an extremely important notion in algebraic geometry and plays multiple roles. Let me just emphasize two of them. So one of them is kind of it plays an important role in connecting different subfields of the subject to each other and having them talk to each other. It's some kind of a bridge between areas. So I'm referring to Grothendieck's motivic philosophy, and this is more of a yoga than an exact science. It helps you generate predictions on one side using knowledge you have on the other side, but then you have to prove them by other techniques. And the other role I wanted to mention is much more down to earth, which is that it plays, often when you're trying to solve a geometric problem, you can encode the abstraction to solving that problem in terms of a cohomology group. There'll be like an element of some cohomology group, and then if you can prove by some other techniques that the cohomology group vanishes, then the abstraction is 0, and then you can solve your geometric problem. And so what I want to talk about today is an example of the latter, but also the former in some sense. So I want to talk about a vanishing theorem in algebraic geometry in the p-adic world and some geometric applications it has. But the result and the statement itself were both motivated by this analogy between complex Hodge theory and p-adic Hodge theory. And so I want to also try to convey that as we go along. And so let me begin by telling you sort of just the classical story over the complex numbers first. So just so we're on the same page, let me set things up. So x is going to be, for now, a smooth projective variety over the complex numbers. If you like, you can think of it as a compact complex manifold with a Kähler structure. And E is going to be a vector bundle on X, which, again, there are two ways of thinking about it. You can either think about it purely algebraically, or you can think about it as a holomorphic vector bundle. They're equivalent. And so attached to this data, we can define some cohomology groups. H star xc is the notation. It's the cohomology of X with coefficients in E. Again, you can define this purely algebraically. It's the kind of thing that you could actually tell a computer to try and compute if you had equations for your variety and your vector bundle. It also has an analytic definition. And the theorems I'm going to talk about concern vanishings of some of these groups in certain situations and the consequences they might have for actual geometric problems if you didn't care about cohomology. And so let me begin with perhaps the most classical instance of a vanishing theorem, which is Sayre's vanishing theorem. So it's the following statement. So let's say our projective variety is actually given to us as a projective variety. So it sits inside the complex numbers with an embedding. And my vector bundle is the tautological bundle on projective space O of 1 restricted to X. And since it's actually a line bundle, let me call it L. So in this setup, Sayre's theorem is the following statement. It says that the higher cohomology of X with coefficients in tensor powers of L, L tensor n, is going to be 0 if n is sufficiently large. So maybe I should just make some comments about this. So this is not a super deep theorem nowadays. First of all, it has nothing to do with the complex numbers. There's a version of this. I mean, the same statement is true over any field or even any ring or whatever generality you want to work in. It's a purely algebraic statement, and it has a purely algebraic proof. And it's a little hard to give some concrete geometric applications of this because it's kind of baked into the foundations of the subject. Like you can't, at least I can't imagine, like giving a first course on projective varieties without having this show up very early. But let me still try to convince you that this is capturing some interesting information. And so here's kind of one application, maybe, of this result. So let's say X is a Riemann surface, compact, or an algebraic curve, if you're thinking algebraically, of genus G. And so here's a picture, I guess, in genus 2. And let's say I give you a bunch of points on the surface, x1, x2, x3, so on up to xn. In this context, you might wonder about the following question, which is, what is the dimension of the complex vector space spanned by the following functions? So f is going to be a meromorphic function on X. So it has poles at finitely many points. And I'm going to declare that the poles are at the X size, and they're at most simple poles. So poles of f belong to the set of x1 through xn and are simple, meaning at most simple. Could be no poles. So kind of by basic theorems in complex geometry or algebraic geometry, this vector space is actually finite dimensional. It has a name. This is h0 of x with coefficients in some particular line bundle, which I'm not going to tell you about, which is sort of related to the xi's. And maybe I should call this L sub n. And then the Sayre vanishing theorem together with Riemann rock gives us an asymptotic formula for the answer. And it says that the answer is given by just the number n plus O of 1. So asymptotically in n, there is one extra function each time you allow one extra simple pole. And so this is the kind of information that I mean that cohomology captures. This is a statement that concerns higher cohomology groups. And because they vanish, you get to conclude something interesting about the low degree cohomology groups, which have a concrete geometric meaning. Great. Are there any questions so far? Sorry? I mean, it's like n plus a constant. Sorry. OK, Ofer is offering a different proof of this theorem. Yes. Wait, sorry, I should have asked this earlier. Do I just push this up? OK. Right. So that was kind of an easy example. And as I said, it's a purely algebraic assertion, which doesn't have much to do with other fields of math, I guess. But now I want to mention a different vanishing theorem, which is kind of the one I want to focus on today. So this is the Kodara vanishing theorem. And this is now specific to the complex numbers. The proof uses some analysis. So let me just say x and L are as above, meaning x is the projective variety, smooth, L is an ample line bundle. And instead of sort of providing some asymptotic statement, like in Serre vanishing, it'll actually make a precise prediction. So it says that the cohomology of the inverse of L, so let's say h less than d, d is the dimension, of x with coefficients in the inverse of L, so the anti-tautological bundle, is 0. And this is equivalent to a different statement, which is h. So there's something called Serre duality, which allows you to formulate this slightly differently, which is the cohomology of, in positive degrees now, because duality sort of switches I with d minus I. So omega x tensor L is 0, where omega is the canonical bundle, so it's the bundle of top forms on your variety. So this is some statement, and if you first look at it, maybe it's not clear what exactly this is capturing. And so I wanted to give you at least one example of what's going on, or how you might use such a theorem. So maybe application. So I'm going to put myself in a situation where, so maybe I should say first the moral of the story. Is the moral somehow is you may produce sections. So of omega x using this theorem by some kind of induction on dimension. And so let me just try to explain this. So say I have a hypersurface in my variety. So it's the vanishing locus of some section of this line bundle L inside of x. And so picture is something, you have x over here, and you have this codimension 1 subvariety h. And S is a section of L, meaning if you're imagining L is just the pullback of O of 1 on projective space, then this is just a hyperplane section. You take a hyperplane on projective space and you restrict it. And then what the theorem tells you in this setup is the following. So theorem implies that a certain map is surjective. So let me write what the map is. So I can look at the global sections of the canonical bundle, omega x, and I have to twist it slightly. So I twist it up by, I guess this just means tensor with L. So maybe let me write it. Well, sorry, it's easier to think about it like this for the map. So let me leave it this way. If you have such a section, so I'm looking at sections of omega with at most simple poles along this divisor h, I can look at the residue of such a form, and I get a section of the canonical bundle of the divisor itself. I guess sorry, I should have put 2h over here because I want h on this side. And the section of the section that you get on the divisor has at most simple poles, because over here I put this 2, which meant the poles have order at most 2. And the theorem implies that this map is surjective. So maybe the precise numerics doesn't matter. What I'm trying to tell you is it's giving you a recipe to prove some kind of a statement along the lines of there are lots of sections of omega by induction on dimension. Let's say you solve that problem for the hypersurface, and you produce some sections over here. The theorem says this map is surjective, so then you can lift them, which means you have some data, some geometric data on H, and you can now spread it out to all of X. And so this is very useful in proofs where you do induction on dimension to prove, let's say, the canonical ring is finitely generated, this theorem of Burke, Arkoskini, Hick, and McKernan in birational geometry, because it's allowing you to sort of drop the dimension and work by induction. So this is the kind of application of Carrera vanishing I want to emphasize right now, because it was also partially at least what motivated what came later. Great. Are there questions so far? Right. OK. So we have this theorem. I told you maybe some way to use it to produce sections. Let me talk a little bit about what goes into the proof. I don't want to spend time on the proof, but there are multiple proofs of this theorem by now, and they all use some form of Hodge theory. So the most classical proof, which is Kodaira's, definitely uses Hodge theory. There are sort of more modern versions of that argument which still use Hodge theory. And there's a characteristic P proof by Deline and Luzy, building on a bunch of other work, which also uses some form of Hodge theory, but now in characteristic P. So it's not like stair vanishing, but it's just kind of a pure algebra statement. And so let me just say roughly what the proof idea is in one line, just to explain where the topology comes in. So you use Hodge theory to translate theorem, or to deduce the theorem, I guess, into a topological statement. And the topological statement is the following. So you look at the cohomology of an affine variety of dimension d with coefficients just in the complex numbers. So usual singular cohomology, nothing fancy like this vector bundle stuff. And then the theorem is that these groups vanish. So this is called the, I guess depending on how you're trained, it's either the Arden vanishing theorem or the Andreotti-Frankel vanishing theorem. But it's a purely topological statement about the topology of affine varieties. And the point is that this kind of black box of Hodge theory is going to allow us to translate this kind of algebraic statement into this topological statement, which we can then study via other techniques. And essentially what I want to try and do in this talk is explain some analog of this process for a different kind of Hodge theory. OK. Hello. OK, so let me formulate the question I want to try and address in this talk, which is, what happens if you try and take the statement of Kodaira vanishing and imagine variants of it in other kinds of algebraic geometries? So what happens to this theorem, the one up there, over, say, a finite field, or even over Z? So if your algebraic variety has coefficients, the defining equations of coefficients in a finite field or the integers, you can still talk about these groups. They're perfectly well-defined, purely algebraic constructions. But clearly, this proof is not going to apply, because I'm using something specific to the complex numbers there. And so the question is this theorem still true? And if so, how would you prove it? So let me first immediately tell you that it's not. So there's a problem. Is that this is not true. So as stated, it fails. So there's like a small industry now of producing counterexamples to this. But I think some of the ideas go back to work of Mumford, and I think maybe Raynaud produced the first example where something was smooth. There's work of Ramanujam, and lots of other people. So at this point, you might just declare defeat and want to move on, do something else with your life. But I wanted to point out that if the goal was to have some application like this, where you are producing a lot of sections, it's not quite necessary to have this kind of a strong vanishing theorem. If you sort of go through the argument to produce sections, you need something weaker. In particular, it's enough to prove this vanishing theorem not for x itself, but rather some kind of a cover of x. Because once you produce sections up there, you can trace them back down to produce sections downstairs. And so this is kind of the idea that we want to follow. So the idea to get around this problem is work up to finite covers. And so let me at least give an example of why this is semi-reasonable, which comes from topology. But the idea is that if you're working over Fp or over Z, these cohomology groups are also Fp vector spaces or Z modules. They could have torsion. And so this is a question about torsion cohomology classes. And what this idea is saying is torsion cohomology classes can often be annihilated if you pull them back along finite covers, unlike cohomology classes which have coefficients in a field of characteristic 0. And so the simplest example of this is the following. So this is a purely topological statement. So let me say x equals S1. Then H1 of x with coefficients in Z mod P is the cohomology of the circle with mod P coefficients. And so it's just a one-dimensional vector space over Z mod P. It's non-zero. But there are finite covers of the circle where this class can be annihilated if you pull them back to it. Namely, you look at multiplication by P on the circle itself. So if I look at the multiplication by P map, or I guess raising to the Pth power, depending on how you think of the circle. So Z goes to Z to the P. So this map has the property that the pullback annihilates this group. Because it induces, I mean, for any coefficients I put over here, the pullback is going to have the property that is multiplication by P, because I'm multiplying by P on the group. And multiplication by P on Z mod P is the 0 map. And so this annihilates this group. And therefore, if you're imagining that this group is capturing some kind of an obstruction data to solving certain geometric problems, then what this is suggesting is that maybe you can kill those obstructions by passing from X to certain finite covers of it. And this is the idea that we want to follow in algebraic geometry. OK, great. Are there any questions so far? So let me explain now what the statements are. So this is a version of Kodaira vanishing in mixed characteristic, meaning over something like Z. I will also comment on the case of mod P coefficients in a moment. But so let's fix a prime number P. I guess I was implicitly doing this in the previous discussion. And so whenever you have a prime number P, let me say what I'm trying to do verbally first. Instead of studying the problem over Z, I want to zoom in on the P primary part of the problem. And so I want to try and understand what are the P torsion classes that cause problems and try to annihilate them. And so for that, I might as well work in a setting where P is the only interesting prime number. Everything else has been inverted. And so I'm going to work over the p-adic integers, which is one way to accomplish that. And so I can define something called ZP. It's the ring of p-adic integers. It's a completion of the integers for the p-adic metric. If you haven't seen this before, feel free to assume I've just taken Z and inverted all the primes that are not P. For the purposes of this talk, nothing will be lost if you work with that ring. It has the feature that you can mod out by P, and you get a finite field Fp. But you can invert P, and what you get is a field called Qp, the field of p-adic numbers, which is a field of characteristic 0. So it can be embedded inside the complex numbers, non-canonically at least. And so it's some kind of a glue that you can use to connect things happening in characteristic 0, which maybe can be understood by a Hodge theory, versus things happening in a kind of pure characteristic P setting. Okay. And so I think I can actually formulate the theorem right away. So let me do that. Maybe let me call this theorem A. The setup is going to be the following. So x over the p-adic integers is, let's say, a projective variety. For the experts, I mean, it's flat over ZP. The picture is something like this. Here's x. You imagine that ZP is basically a line, although it's hard to picture it because the associated geometric object has only 2 points. But anyways, let's draw it as a line. And so here's kind of the special point corresponding to that field FP. And you have some variety over here. And you have kind of the point corresponding to QP. And you have some variety, which may be slightly nicer than what you have over FP. So these are kind of the two varieties you have in the picture. They're related to each other through this gadget called x, which is living over the integers, p-adic integers, ZP. And L is going to be ample line bundle on x. So again, it could be of the sort that we had earlier. It was up there, it's the pullback of O of 1 under a projective embedding. Weaker things suffice, but I'm just trying to give you a flavor of the statement. And so then what the theorem says is it's not going to be true that the groups that are showing up in Kodaira vanishing are actually 0 in this setting. There are counterexamples to that. I think the first one for something like this was written down by Totaro. But we want to sort of annihilate it by passing the finite covers, like I was suggesting over here. And so that's exactly the statement. So there exists a finite cover pi from y to x such that if I pull back along pi, so this is a map that goes from the cohomology of x with coefficients in L to the k, say. I'll say in a moment what k is, with torsion the torsion part of the cohomology, going to the analogous thing on y. So the statement is that, I guess maybe I should try to fit the statement here to keep the theorem on one board. So pi upper star torsion is the 0 map for k being -1, 0, or 1. So for both positive and negative powers, and in fact the 0th power, you can annihilate the sort of bad classes, the classes that wouldn't be there if Kodaira vanishing were true, by passing to these finite covers. And so I will discuss this a little more. But so the k equals -1 case is what corresponds to Kodaira vanishing in this setting, because it was about negative powers up there, the first statement on that board. The fact that you can also prove something for 0 and 1, it's some kind of an arithmetic phenomenon which doesn't really have a complex analog. Finite surjective map. Yeah. Right, so it's not unramified. I mean, it's not like a covering space, because there are sort of simply connected varieties where you have these bad cohomology classes. Other questions? Right, so, sorry? Well, so if you invert P in these groups, you get something that sort of falls under the purview of Kodaira vanishing. So those classes wouldn't be there after inverting P. And so we only somehow care, like the classes that are causing problems are the torsion classes. There are sort of better statements you can make. I think this was just the cleanest I could come up with. Correct. Well, I think what I wrote on the board is correct. Yeah. Okay. Right, no, they're not. And so this is also saying something about singular varieties in characteristic 0, which is that if you take those classes that are there in characteristic 0 because of singularities and then spread them out to mixed characteristic, Well, they won't be torsion, but there's a different version of this theorem which will tell you that you can make them p divisible by going up to finite covers. So sort of p-adically, they become small as you go up. Other questions? Right, sorry, so maybe I should have formulated it slightly differently. Like, there's also the other change over here that I have all cohomology degrees instead of just all but one as up there. And again, that's related to the fact that I'm looking at the torsion classes. So if you try to understand torsion classes in some degree I via some kind of standard exact sequence, that's going to be related to cohomology with mod p coefficients in a different cohomological degree. And that's sort of what allows you to get a cleaner statement this way. So let me make a remark about this. OK, so I started off by saying what happens over fp or over z, and I just told you something about the integral situation. This doesn't cover the mod p case, but the mod p case is actually much older. So the analog over fp of this theorem, I mean, correctly formulated, is due to Hochster and Hunicke and Karen Smith. So this is from the 90s. And this is definitely what inspired me to think along these lines. And in this case, it's actually maybe slightly easier to explain what is going on. And so let me give an example. So let's say x is the favorite variety of a lot of people in this room, probably, an elliptic curve. Over fp. So in this case, there's one interesting cohomology group, which is h1 of x with coefficients in OX, the structure sheaf. It's a one-dimensional vector space over fp. So I can ask how would I access it using finite covers, or how would I rather not kill it using finite covers. And in this case, it's easy to guess what the answer is. It's just like the picture for the circle. The elliptic curve has interesting endomorphisms, and I can use those endomorphisms to solve my problem. So again, multiplication by p on my curve does the job. So pull back along, multiplication by p is the zero map on cohomology. But this also suggests that this is going to be hard to do in general, because most varieties do not have interesting endomorphisms. So you're not going to be able to just write down some endomorphisms to solve this problem. In characteristic P, I should have amended that. Sorry. In characteristic P, every variety has one interesting endomorphism, which is the Frobenius endomorphism. And so the Frobenius endomorphism can be used to solve like a big part of this problem in characteristic P, maybe not entirely. So in the elliptic curve case, if I used Frobenius over here, it would solve the problem in the supersingular case, but not in the ordinary case. But anyways, in characteristic P, you have at least one tool to get started, which is the Frobenius endomorphism. And that was kind of what was missing in this mixed characteristic world. There's no analog of the Frobenius, and so we're kind of stuck for a long time. Right. The other comment I wanted to make was related to Lars's question, which is that ramification is absolutely necessary. So these covers are not unramified. There'll be simply connected examples where you want to apply this theorem, and then you're forced to introduce ramification in this map. OK, so that's the theorem. This version of Kodaira vanishing and mixed characteristic. It has several applications, but maybe I'll only mention one of them. So when I was talking about Kodaira vanishing in characteristic 0, which has now scrolled off the board, maybe I'll bring it back. So I mentioned that application up there, which was to producing lots of sections of the canonical bundle. And producing lots of sections of the canonical bundle is something you want to do in birational geometry, because you want to prove things like the finite generation of the canonical ring and so on. And now that we have a version of Kodaira vanishing in mixed characteristic, you might want to try and do something similar in that context. And there is at least one result along these lines. And so this is a theorem. It was independently due to two groups. So there's a lot of names involved. I'll just write acronyms and say them out loud verbally. So OK, so that's Takamatsu and Yoshikawa. That's me. That's Lin Chuan, who's sitting in the second row. Zsolt Patakfalvi, Carl Schweid, Kevin Tucker, Joe Waldron, Jakub Witeczek. And the theorem essentially, very informally, is the following. So one can run the minimal model program, which is some kind of a surgery for algebraic varieties over Z. Or actually, I should say Z adjoint 1 over. We have to stay away from 1, 2, and 5. So Z adjoint, 2, 3, and 5. So 6 times 5, 30 in dimension 3. The fact that dimension 3 is important is that one of the key ingredients in all this work in birational geometry in characteristic 0 is resolution of singularities. And that's, as far as I know, still open. So that's where that abstraction comes from, and this is related to some other techniques. But at least we have sort of some handle on the birational geometry of threefolds in mixed characteristic, meaning surfaces over the integers. Right, so I was going to, so there's other applications I could mention, but some of them are probably beyond my expertise. So I was surprised to learn recently that this result and some consequences of it are useful in solving the non-Archimedean Monge-Ampere equation, which I know nothing about. And so I was very happy to hear that. This is work of, let me make sure I get the names right. Fang, Gubler, and Kuhnemann. So I don't want to talk further about applications of this theorem now. I want to give you tell you a little bit of a story about how this came to be and what other things it's related to. And so I want to first talk about a local variant of this result, which was somehow actually came first and maybe is easier to grok because unlike the theorems I've mentioned so far, there's a version of this statement which doesn't involve any cohomology whatsoever. It's just an explicit statement about elements. So this is local Kodaira vanishing. And so to motivate this, I want to draw a picture for why there should, in fact, be a local analog of this global-looking result. And so it's the following kind of analogy that motivates us. So if you have a variety sitting inside projective space, there's a sort of standard picture one attaches to this situation, which is the following. So here's X, say. Since X sits inside projective space, there's a tautological bundle O of 1, the bundle of lines parameterized by this projective space over X. And so let me draw it like a cylinder. So this is the total space of O of. Now to get my normalizations right, I think it's -1 I need to use. This maps down here. It's a line bundle. The fibers are lines, and it's a non-trivial line bundle as you twist around. So the picture is not exactly correct, but it's the best I can manage. It has a section, which is the 0 section, like any line bundle does. And the choice of -1 over here tells me that this 0 section is actually contractible in the world of algebraic varieties. I can squish it down to a point without changing anything away from that point. So I get to build a cone like this. And this is nothing other than the cone the affine cone on the projective variety itself. But the point is that this is affine, and moreover, it's conical. So there's a scaling action. And so all the action on this variety is happening near 0 in some local neighborhood of 0. It's a cone singularity. And then the principle is roughly, let me write it over here, that the projective geometry of X is closely related in some sense that can be made more precise, to the affine geometry of the cone. And so what I mean, for example, is that if you have a statement on the left-hand side, like Carrera vanishing, which is a statement about certain cohomology groups, it can sometimes be translated to statements on the affine side. And once you're on the affine side, you can ask yourself, well, is it specific to the cone situation? Or could it actually be true for any affine variety? And so this is an example where life works out in your favor. And so there's actually a local version, which is true in general, without the cone assumption. I don't know what this is. Sorry. And so let me actually tell you what the local version of Carrera vanishing is in this world. So I'm going to formulate it in two ways. One of those is sort of more conceptual, but it involves some kind of an infinite construction. And the other one is much more elementary in terms of, as I said, explicit elements. So the setup in the local version is the following. So R comma M is an excellent Noetherian ring. I'll say in a minute what I mean. And P is in the maximal ideal. So local. So local just means it has a unique maximal ideal. It corresponds to the fact that geometrically, we only care about all the action happening near a point. And so we might as well throw away the other points, which you can do in algebra. Excellent is actually, despite the name, an extremely mild condition. And you really have to go hard, search hard for finding non-excellent rings. So let's ignore that. This is the kind of the most basic finiteness condition in algebraic geometry, similar to working with like a manifold as opposed to a random topological space. And the key assumption is that P is in the maximal ideal, which means that R mod M, which is a field of characteristic P. And I will give an explicit example of how such a ring arises in a moment. But let me formulate the theorem first. So in this situation, actually, let me simplify my life and assume it's a domain, not just a ring. So there are no zero divisors. X in the Noetherian local domain. So in this situation, there's an operation which is analogous to taking the algebraic closure of a field. It's equally canonical or non-canonical. So it's the integral closure of your ring in an algebraic closure of its fraction field. So it's about as well defined as the algebraic closure is. It's unique up to isomorphism, not up to unique isomorphism. It's some huge object. It doesn't have good finiteness properties. It's some kind of a bookkeeping device for keeping track of all possible finite covers simultaneously. But the theorem is essentially that despite its hugeness, it actually has some really nice commutative algebra properties. So R plus mod P, if I look at this ring, then it's Cohen-Macaulay. And so, OK, I owe you a bunch of explanations over R mod P. And so Cohen-Macaulayness is kind of one of the nice properties that a commutative ring can have. It's analogous to saying that the singularities are not too bad. So it's not quite like a smooth manifold, but it's sort of an approximation to that. And so, OK, for people that don't know what these words mean, let me formulate the statement completely elementarily. So equivalently, this is really saying something very concrete. So let's say R is a finite extension of the formal power series ring over the p-adic integers. So I can form formal power series over any ring, including over the p-adic integers. And let's say I have something finite over it, meaning each element satisfies an integral monic polynomial over the subring. Geometrically, this is some analog of choosing a Noether normalization. And I'm only doing it to make to make it possible to formulate some statements. It's not necessary. So in this setup, so in this ring, the xi's are sort of as independent as you expect. Like there are no interesting relations between them. But there could be some interesting relations on this side. And the theorem is essentially saying that whatever those are, they will die if you extend R further. So if you make it slightly bigger. So then there exists a further finite extension R inside S such that the following holds true. So any, let me say, bad relation, or well, I guess I can just say any relation. So the good ones are fine anyways. Any relation of the form summation Ri xi equals 0 in R mod P. Because R was essentially arbitrary, there can definitely be sort of interesting relations like this. The statement is that they become trivial in S. And so what do I mean by trivial? So there is an obvious relation in the picture, which is xi times xj is xj times xi. And the theorem is saying that essentially every relation is a linear combination of those relations if you allow yourself to go up to S mod P. So this guy is saying it's a linear combination of something like this. So I mean, technically what I'm saying is that the xi's look like a regular sequence. So this is the elementary form of this local vanishing theorem, which was a local form of this global vanishing theorem. I don't know, and I would be interested in knowing an elementary proof of this when I think n is at least, actually even when n is 2. I think when n equals 1, the theorem is kind of easy. But if n equals 2, I think the proof uses essentially everything I know in p-adic-Hodge theory. OK, so that was my attempt at telling you about an elementary version of this theorem. Are there any questions? Yeah, so Heidman proves the almost version of this statement. So he proves something like this up to multiplying by a small power of p. So the old result doesn't account for all torsion classes. The old result says that any cohomology class can be made p divisible, and torsion classes in degree at least 2 or 3 can die. But in small degrees, I didn't know how to deal with torsion before. But also, like, there's a relative version of this theorem, which I didn't formulate here because of the kind of talk this is, and that was completely inaccessible previously. Other questions? OK, while I find my notes, feel free to ask. Guess not. OK, so this theorem has some applications in commutative algebra. Since I have only 10 minutes, maybe I don't want to talk about the application, but I want to go back to a promise I made you at the start of the talk, which was that this was going to be an example of 2 uses of cohomology. One was as a kind of tool for solving geometric problems, which I tried to indicate via this kind of lifting sections and birational geometry stuff. But the other was it provides some kind of a bridge between different worlds, between like the complex world and the p-adic world. And so I want to try and give you some very brief indications of how the proof works, not in any kind of depth at all, but just to indicate where the ideas come from. So I guess maybe the question I'm trying to answer is that why is this proven now as opposed to 20 years ago or 30 years ago? And the answer is there are basically 2 tools that are now available, which weren't available before, both of which were inspired by thinking about kind of things happening in other areas of math. And so let me just comment on that. So the proof has 2 main ingredients. I think Mike alluded to both of them when he introduced me, but maybe I'll mention them again. So the first is, this is joined with Jacob Lurie, which is a p-adic version of the Riemann-Hilbert correspondence, except it's not quite a correspondence. So it's a p-adic Riemann-Hilbert construction, let's say. And let me say concretely what I'm trying to do here. So it's a p-adic Riemann-Hilbert construction for mod p sheaves on an algebraic variety in characteristic 0. So for fp sheaves, unlike complex Hodge theory, which deals with complex sheaves on variety in characteristic 0. And so obviously, I'm not going to be able to formulate a precise statement, but let me just say where this comes from. So Jacob and I were not trying to solve this problem. We were motivated by some analogies with complex Hodge theory. So in complex Hodge theory, there's this amazing work of Saito, Morihiko Saito, on mixed Hodge modules, which gives you some kind of a package which is very similar to what Bailenson, Bernstein, and Deligne provide with perverse sheaves over a finite field. And so in Saito's theory of mixed Hodge modules, you get kind of a notion of there's sort of good D modules on a complex algebraic variety. And they're good in the sense that the D modules themselves and their graded pieces and so on have some really nice commutative algebra properties. And these properties are quite useful in algebraic geometry in characteristic 0, especially in the work of Popa and Schnell. And so we were motivated to try and find some analog of what was going on there, but where now the coefficients of the sheaves are mod p rather than complex, even though the variety is still in characteristic 0. And so we have some construction. And I just want to formulate one statement you get out of it relevant to what I've written before. And so this ring R plus mod p that is showing up in this theorem, it's something that's accessible using this functor. And so what you get out of it is that this is the functor, the Riemann-Hilbert functor, applied to a certain perverse sheaf. OK, so that's some calculation you have to do. And then there's this general result analogous to what happens in Saito's theory, that if you look at sort of the coherent counterparts of a perverse sheaf, they have good commutative algebra properties. And so this is a general fact, that these things are almost Cohen-Macaulay in a slightly technical sense. So at the level of symbols, I'm trying to prove that something is Cohen-Macaulay. And I'm telling you that this machinery helps us prove it's almost Cohen-Macaulay. And so almost here means that the failure to be Cohen-Macaulay is annihilated by all small powers of p. So it's not quite 0, but the annihilator is huge. So it's very close to 0. So that was kind of step 1. But you still have to deal with the fact that it's not actually 0. And so the second ingredient comes in there, which is the joint work with Matthew and Peter on prismatic cohomology. Actually, I'm presenting this very ahistorically. I apologize for that. And so this is some kind of an integral cohomology theory that seems to do a good job when you're trying to understand integral phenomenon in this p-adic world. And this is an example of an integral phenomenon you want to understand. It can be formulated cohomologically. And so it's not at least completely inconceivable that it would be related to a good integral cohomology theory. That's basically all I'm going to be able to say at this level. But I just wanted to indicate how these things come together. And so this tool itself, again, was not invented to solve this problem. It was motivated in part by calculations of Lars Hesselholt in homotopy theory, and in part by some considerations of Breuer and Kissin on crystalline Galois representations. And so it somehow came as a surprise to me, at least, that you can put these things together to prove some kind of relatively elementary statement. OK. think that's all I wanted to say about the proof. Are there any questions?
Your Riemann-Hilbert correspondence, so what, if you associate the ring to stability?
Well, the ring, the output happens to be a ring in this case because the perverse sheaf has some extra structure. But in general, it's a module. So you start off with some kind of constructible sheaf on the generic fiber of your variety over ZP. And the output is something that lives that's a coherent sheaf on the special fiber. So spec of R join 1 over P. Other questions? OK, so I have, I think, 3 minutes. And I'm clearly not going to try and do something super challenging. But I wanted to end by formulating a question, which is sort of, with collaborators, we've been thinking a lot about extending some of these ideas to prove more results in birational geometry. And certain rather thorny questions come up. And I want to just formulate one of them to give you a flavor of the kind of problem you need to solve. So here's a question. And I try to keep things as simple as possible, but OK. So say R is a p-adically complete Noetherian excellent ring, just like over here. OK, and since Ofer is in the audience, let me say with a dualizing complex. Sorry? If you're happy that I'm going to move on. So in this setup, what goes into actually proving these results and sort of using, like I mentioned some ingredients, but I didn't explain how they come together. And so one of the objects that you need to understand is the following. So let me call that tau omega r. It's going to be an explicit abelian group or a module you attach to such a ring. And it's defined as follows. So it's an infinite intersection over all finite covers of R. So R plus was some kind of a union of all finite covers. And so I tried to approximate it by actual finite covers, call them S. And then what I can do is I can look at the trace map from the dualizing module of S down to the dualizing module of R, and then take an image. So this is, in some sense, dual to just the fact that R sits inside S. And so I'm sorry, Lars, because I'm taking an image, but this is what we need to do. And the issue with this definition is that it's an infinite intersection. So you need to wrestle with the fact that things are not going to work super nicely, or you have to somehow tame the fact that this is an infinite intersection. And so the basic question that we still don't know how to answer is whether or not this object commutes with localization. So does R maps to tau omega r commute with inverting an element, say? Or, yeah, commute with localization. It's a submodule. I guess I didn't write this explicitly, but it's a submodule of omega r. So it's a reasonable object. This is a finitely generated module. And so this is also a finitely generated module. It ought to commute with localization. But the infiniteness of the intersection makes it rather tricky to handle. I will just mention some evidence for it and then stop. So the evidence is the following. So first of all, this is true in Kersig P. I guess this is essentially the work of Karen Smith. Is that right? Thanks. And then what we can do, this is sort of in progress by the same 7 authors that were somewhere on there. So BMPSTWW in progress. Is in mixed characteristic, we prove it up to p torsion. So true up to p torsion, or even in some stronger sense, like up in the almost world for the experts. And so this uses, again, the Riemann-Hilbert functor. And somehow the key point, and this is my last line, is that essentially this object that I'm defining, the way we proved anything about it is we identified with something else, which is more finite in nature. And it's the Riemann-Hilbert functor, essentially, applied to the IC sheaf on the generic fiber with mod p coefficients. So this is the intersection cohomology complex, and then I'm probably missing a shift. And this is up to, this is in some almost sense. And that's where this up to p torsion comes from. And so essentially what I'm trying to say is that if you understand stuff about intersection cohomology complexes in Kiersig 0 with mod p coefficients, you have some hope of understanding this object, but only in this p almost sense. And it would be really nice to me if there's a way to write this exact statement without any of the disclaimers I put around it. But I don't know how to do it, and I'm out of time, so I'll stop here. Thank you.